Hello, hello. Today we are going to try to create oscillation. So we will be using these 5x5 timers here from Texas Instruments. It's the NE555P in this beautiful dual inline package with 8 feet. And the special thing about it today is that I'm trying to do the wiring all from the top of my head with no documentation. And so let's see. So first we have to watch the notch up here. You see it, this little half notch. So we know this is then pin 1 to the left of it, and we can start inserting it here. So, and perhaps we can get a little bit closer also here. And then we have to just be aware where the positive and negative input has to be, and that is pin 1 and 8. Yeah, and I already had to cheat a little bit because I didn't know. So now I know pin 1 is negative. So let's put some pliers here. My good old pliers. Very cool, very cool. So let's put the negative rail is, so we need pin 1 is up here. So we going to put the negative rail here, and then the positive rail, and I use red for positive supply voltage. So I'm a good boy doing the color coding like it should be. Hey, and there it is. We have negative on pin 1 and positive on pin 8. Yeah, so supply voltage is up. So, but that's only not half the rent. We have to do now the good stuff. And for that, as you know, we need 2 resistors and a capacitor. And the trick is that the 2 resistors and the capacitors will give us the time constant for how long our oscillation will be, or how high or how low our frequency will be. So let's choose. But now we don't care about values so much. We just want to have some oscillation, and we want to see things first, and then afterwards, if we want to have higher frequency or low frequency, we can adjust that. So let's do it first and think about it afterwards. So where are my resistors? The one I'm looking for, something like, yeah, let's see, the time constant is always, the frequency is always lower when you use higher higher resistors and higher capacitors. And you get the frequency lower. And what we actually want to do is see a LED blinking, so we can, it would be wise to choose pretty high values for the start. Let's say, what do I have here? 3K3 resistors, okay, should be good. So let's do one of them. So you see here, I found a 3K3 resistors. So you know, red is 2, orange is 3, and yellow is 4. I think it's a nice color coding because, you know, red is 2, you know, red is the darkest one. Then if you think about it, orange is a little bit lighter, so it gets to 3, and then yellow is lighter still, and it is 4, and it makes kind of some sense in that order. Red 2, orange 3, yellow 4. But just a side note, So let's make here the legs nice 90-degree angle. And now the first 3K3, we have to put it between 4 and 6. As you know, I'm using no documentation here, that's all top of my head. So we're going to put it between 4 is here, and then 5, 6, 7 is here. No, between 4 and between 4 and 7. So between 4 and 7, first resistor. The other thing is that we're going to use a 3K3 resistor. So 3,300 ohms. We'll use one. Also for the connection between, let me think, what was it? That's the learning by heart part. I think it was between 6 and 7, yeah. 6 and 7. So this is 5, 6, 7. This is these two. All right. And now some specialty. So the components that determine our frequency are nearly done. We have the 2 resistors in place, 2 times 3K3. But now the capacitor is needed. I have this nice box here, and let's choose something around, yeah, let's say the 100 micro. How big is it? Oh, the 100 micro is pretty big. Doesn't fit nicely into the schema. What is this? Yeah, 10 microfarad, 22. 22 gets to look ugly, so let's use 10 microfarad. As I said, we will think about that later. We're just building stuff now. And then this is an electrolytic capacitor, so we have to watch out here. It says, hey, on the minus side. And so I remember by heart that we have to go with the capacitor from pin 6 to ground. So that is our positive supply rail, and we'll use that as a negative supply rail. So let's put the negative side here, downwards facing, and now the negative side from 6 to ground. That done. Okay, now the frequency determining components are set. Now it's just a little bit of a hexy thing, because we need to do some wirings for the 555 NE 555P from TI, and namely that is that pin 4 needs VCC. It needs the supply voltage, not ground, but the supply voltage here from actually afterwards I'm going to support these rails with what I am layouting here. So I have now determined this rail here will be on VCC afterwards. So we have pin 4 on VCC, very good. And I think the last thing we need is the magic connection between pin 2 and pin 6 here. Pin 2 and pin 6 connected. I have a nice, we need only, I'm looking for a size of jumper wire that connects these things in a good manner. So I think this one is a nice size of jumper wire. So let's use it and connect pin 6 here. Put it in, zack, and pin, oh, we have to bend it a little, I think, pin 2, zack. We have to watch that perhaps these resistors legs don't touch. That is cool. Perhaps we also can ensure that by putting this black wire through the 2 resistor legs, and then this acts as an isolation between the 2. Just a little, but it's still the same layout. So 2 and 6 are connected. Okay, what we haven't connected yet is pin 3, but I tell you now that will be our output, the output that we want. So this one will be alternating between 0 and 1. So let's say low, high voltage and high voltage of our system. So pin 3 is really the desired output pin that we all we did now was to have pin 3 giving us some kind of alternating output. So pin 5 is not connected, but that is true, I think. Pin, if I remember, so that's the top of my head pop. Pin 5 is the only one not connected. Pin 6 is connected to pin 2, and from 6 to 7 with the resistor from the frequency determining components. Pin 7 is connected with pin 4, very good. And then I forgot to say pin 6 is from the capacitor connected to ground. And pin 8 is the positive supply voltage pin, and I think I got it right. So let's just hook up the positive and negative rails. I'm doing this with a few jumper wires out of my jumper wire box. So what do we use? We will use 5 volts because the NE555 from TI, it works with, I think, starting from 5 volt if I'm right. So let's build things first and think about it later. And then I need to connect, where is my ground rail? Up here. So it's a nice prototyping board I have from, company is called Global Specialties, and the product is called Protoboard, also abbreviation PB for Protoboard, and then 503. This has all nice features, it's really cool. Haven't used it too much though, always having built stuff on my breadboards without the help of such external instruments. Like, it has a function generator really, so we could output a sine wave with a certain frequency and something. But as you see, we are building now here a square wave, and we're using the 555. Yeah, that's also cool, but there will be videos with other things too. So now I have corrected the side to the ref to the right now with the supply voltage. Now I'm connecting the left side. So again, I'm using VCC on here the left side. And then the last thing missing is the ground connection to the inner rail. I have a black jumper wire. As you know, these are called also Dupont wires or Dupont wires. These are pretty cool. You can also make it, construct them yourselves. I can share a video about this. In fact, I already have made a video about this. You can watch that if you want. And then, just for the sake of cleanliness, I'm going to change the colors up here where you don't see. It's for my personal. I can go down with the wires so you see them a little bit. Here, positive, negative, and here, positive, and here, negative, ground. The only thing you have to watch is that these outer rails here, the 2 columns going up and down here, these terminate at the screws. So if you want to have ground or VCC down here, you have to make a little bridge in between these two. But once you know it, it's okay. You can then, like you want to have ground supply down here, you have to make such a little bridge in here. And then you can extend your layout downwards here to this area here. But nope, we are not doing this now. Yeah, and to see that this is working, we have to supply here my whole proto board with main supply voltage so that it can do its thing and produce the 5 volt that I want to have. Okay, so let's find a cable. It's really fascinating. Once you need these cables, you don't find them. Do you have the same experience? So funny, I just plugged out my oscilloscope to have such a cable. And turn the power on. And then here. So now the plug is in. I switch on the proto board. I don't know if you can hear the sweet humming. Very interesting. Why does it hum? But it always hummed, so no idea, but it's good. So nothing goes up in smoke. Next good thing. And how can we assert that pin 3, our little nice pin 3 here, does what we want, like oscillate. And as you know, the standard solution for electronics beginners is always the LED, the LED. Let's put first a resistor across there so that we don't harm our LED. I want to limit the current. So what picked I here out of my box? I have this nice box where they offer me LEDs and already together with resistors of certain sizes. So what did I pick out here? So yellow, violet, brown. So I think yellow, as I told you before, is 4. Oh, we have a little focus problem here. No, it's better, I think. 4, 7, violet is 7, I think, 7 or 8. Doesn't matter because it's 4, 7, and then brown is multiplier 1, so we have 470 or 480, something like that. Even if it would be 5 or 6, I don't care. It's around between 450 and 500 ohm of a resistor, and that is always around half a kilo ohm is always a very good. Most of the time, so I don't take my word, but half of a kilo ohm is most of the time is a good value for a resistor, for a LED. Yeah, and now the question is, they said, so we connect now the output pin 3 here to another row of our breadboard. Oh, just my back just dropped magically in the corner. So think what forces were up there. Ooh. Here we connected now the resistor here to this row, and the question is now, if we put a LED in, does the output over the resistor and then over the LED, do we go to a pin that is connected to ground, or do we go to a pin that is connected to VCC? Because then if our output signal is low, then we would draw current from the high pin, because there would be high potential, at our pin low potential, and then current would flow. So current would flow if our pin would be low, if we connected it to high here. So I make it a little bit more intuitive what I say. So here we have anode and cathode. Always here they have a cut end of the LED. and so okay. So you can see this is cut at one and round at the other, and the thing that's cut, that end that is cut, it's the negative pole. So do we connect now here from this row where our resistor is terminating in a moment, to connect it to the positive rail or to the negative one? And I remember both would work, but I remember the documentation sheet of the NE555P from TI said in the schematic that they showed that they just connected it to the positive pole, to the positive supply VCC. And I think I'll do that. And so we have to remember that the positive side of this resistor is this one, the positive side. And then we connect this side to the positive supply. Oh, and you see, what does it do? It flickers in a frequency unknown, but very fast. And so I said we just do stuff and then we think about it afterwards. So when you now see this, we could, so first of all, it's very cool that it's flickering, because that is really what we wanted. We wanted to have some kind of frequency output from this NE555. We wanted to see some output behavior that is high, low, high, low, high, low, high, low. And that is very good. But just to see if this is any kind of rational, so because I said the resistors are frequency determining here, we have to do a little calculation now. So you can watch that when I'm doing that, or you can leave the video if you're not interested, but I think it's interesting. And another thing is that most of the time, or sometimes, it's helpful to connect a 100 nanofarad capacitor over the supply voltage. Also, I learned that from some colleagues, and then I made some experiments, different kinds, not especially for the 100 nanofarad thing, but I had then some for example, some electromotor setup and another setup, and then I realized, oh, okay, sometimes this is not bad and it doesn't hurt. So let's put this this 100 nanofarad cap here over the positive negative supply voltage, just because. And here then it starts to have intermediate breakdowns. So this didn't help, or is it just? It's interesting. It is just in the camera, I think. Does it really have a breakdown in the real world too, or is it just something shown in the camera? No, when I look at the flashing LED, there are no such breaks in it. Okay. So I think that's just some kind of recording effect. Yeah, and let's do the calculations. So to remember, we used here a 3K3 resistor, here a 3K3 resistor, and this is a 10 microfarad capacitor, and with that we'll go into calculations. So let's put that out. Oops, doesn't swing anymore. You swung enough today. So let's use this. So what is it? So to be honest, I think I have to look up the formula from the documentation, because I think it's, so let's see. By heart, I think it's the frequency f at which we're swinging is 1.44 divided by, I think it is the first resistor plus the 2 times the second resistor times the capacitance. And I think the first resistor RA is the one that we connected from 4 to 7, and the one that we are taking 2 times is the one that we have connected as, so this one 4 to 7 connected from the pins 4 to 7. This one is from which you connected from pin 6 to 7, so to say, and that's the capacitor we connected from pin 6 to ground. And then we could continue with inserting values, but let me just check the data sheet if that is still valid, what I know. So yes, hey, that's still true. So we can start inserting values, and so okay, this line here above is good. 1.44 over, so we have 3,300 ohms. We don't care about units now because we know that at the end what has to drop out is from the unit hertz. If we respect milli, micro, nano, everything correctly, we don't have to do the unit juggling. So 3,300 plus now 2 times 3,300, so let's write it out, times yeah, and the 10 microfarad, this is 10 times millimicro, micro is 10 to the power of minus 6, 10 to the power of minus 6, and that is, and to be honest here, I could put it into calculator. I'm pretty lazy, and you know there is this do you know it's Wolfram Alpha, it is called. It's also, you can get it as an app on your so I have it as an app on my iPad. So this is the nice Wolfram Alpha app, and so we can put this in here. I put it a little bit above so you can see everything. So what do we put in here? So always the decimal point is a little bit tricky. I have to use the point 1.44 because we Germans, we do comma for decimal separation, but the rest of the world I think does the point. So divided by 1.44 divided by, I make parentheses, and another parenthesis already, 3,300 plus 3,300, and then times 10 and times 10 to the, and let's also put that in brackets, the minus 6. I think the browser version is a little bit cooler what regards mathematic input because it's neatly formatting also with fractions and stuff, and you have a really nice construct. That's more the calculator view of things. But okay, then they have 1.4 divided by 3,000, but 2 times 3,300, I forgot. 2 times 3,300 times 10 to the minus 6. Let's close the bracket. Oh, and it already says, oh yeah, this is 14.5 hertz around. And but you could also do enter, and what this would say to us, 14.5454545454545454. Periodic 54. This has this down here, period 2. And then, okay, it would also say rational approximation 14 plus 6 11th here. Pretty cool stuff. I like this so much. Also, you can do very much more complicated things with it. Didn't try out so much, but some things it's very tall, very clever. Okay. So we are swinging. What it says is we are swinging at what we saw that the LED was flashing at 14.5 hertz. 14.5 hertz. Which seems pretty rational because it was still visible for our eye. We could still discern the up and off and on times of the LED. So let's see. But this is now all. So you know how to make an oscillating signal now. Very, very cool. And you also, and I think we also rationalized that what we've seen in practice is also to be able to be validated in theory. So the theory is 14.5 hertz, what is rational. Okay, then thank you, and I hope you enjoyed this one, and let's meet the next time in the next video. And if you would like my video and subscribe, that would be not bad. Thank you. Bye.